Welcome back, privacy champions and distributed AI enthusiasts. Today, we're diving into a revolutionary approach to machine learning that keeps your data private while still building powerful AI models. If you've ever worried about sharing sensitive data or wondered how AI can work without centralizing information, you're in the right place. Traditional AI often requires collecting all data in one central server. But what if your data is too sensitive to share, or regulations prevent data movement? Federated learning offers a new path, one that brings the model to your data, not the other way around. Let's explore how this works, and why it's a game changer for privacy and AI. Imagine a world where your personal data never leaves your device, yet you still benefit from the latest AI advancements. The privacy paradox is real. We want smarter technology, but we don't want to give up our privacy. Regulations like GDPR and HIPAA make it even harder to move data around. Plus, with the explosion of data from mobile devices, centralizing everything is often impossible. Federated learning solves this by flipping the script model's travel to the data, not the other way around. This approach is like sending recipe instructions to many chefs, who each learn and improve, but never reveal their secret ingredients. Federated learning is a distributed machine learning approach that trains algorithms across multiple decentralized devices or servers holding local data samples without ever exchanging them. The core idea is simple. Keep raw data on local devices. Share only model updates and aggregate learnings from many devices to build a global model. Think of it as a group of doctors who each learn from their own patients, share insights, but never exchange patient records. This way, everyone benefits from collective learning, but no one's privacy is compromised. The key principle? Learn from everyone, but expose no one. To make federated learning even clearer, let's use an analogy. Imagine a group of chefs, each with their own secret recipes. Instead of sharing their recipes, they each receive instructions on how to improve their cooking. After trying new techniques, they share only what they learned, not their secret ingredients. Over time, all chefs become better, but no one's secrets are revealed. This is exactly how federated learning works in AI. Devices learn locally, share only insights, and everyone benefits from a smarter collective model. Let's break down how federated learning works, step by step. First, a central server creates an initial global model. This model is then sent out to all participating devices, think smartphones, sensors, or computers. At this stage, no personal data is moved. Only the model itself travels. This setup ensures that every device starts with the same baseline, ready to learn from its own unique data. The process is designed to be secure and efficient, setting the stage for privacy-preserving AI training. Next, each device trains the model using its own local data. For example, your phone might use your typing habits to improve a keyboard suggestion model. Importantly, your raw data never leaves your device. Instead, the device creates local model updates based on what it has learned. This means your personal information stays private, while still contributing to the overall improvement of the AI model. After local training, devices send only their model updates back to the central server. These updates are encrypted and aggregated, meaning the server never sees individual data or updates. Raw data remains on each device, ensuring privacy. Secure aggregation is a critical step that protects against data leaks and unauthorized access, making federated learning a trustworthy approach for sensitive information. The server then combines all the encrypted updates from participating devices to create an improved global model. This new model reflects the collective learning from all devices without ever accessing individual data. Once updated, the global model is sent back to the devices, where the process can repeat. Each round makes the model smarter, while privacy is maintained throughout. This process isn't a one-time event. Federated learning is iterative. The model is updated and improved over multiple rounds. Each time, devices train locally, send updates, and receive a better global model. With every cycle, the AI becomes more accurate and effective, all while keeping your data private. This continuous learning loop is what makes federated learning so powerful and adaptable. Federated learning isn't one size fits all. There are different types, each suited to specific scenarios. Cross-device federated learning involves millions of mobile or IoT devices, each with limited resources and intermittent connectivity. Cross-silo federated learning, on the other hand, connects fewer but more powerful organizations, like hospitals or banks, with stable connections and a focus on regulatory compliance. There's also horizontal and vertical federated learning, which differ based on how data is distributed across participants. Transfer learning allows for central pre-training and local personalization. Cross-device federated learning is designed for scenarios where millions of devices, like smartphones or sensors, participate. Each device has limited computational power and may not always be connected to the network. Despite these challenges, this approach enables large-scale learning from diverse data sources. A common example is Google's keyboard suggestion improvements, where your phone learns from your typing patterns without ever sending your keystrokes to the cloud. Cross-silo federated learning connects a smaller number of powerful organizations, such as hospitals or banks. These participants have stable connections and robust computational resources. The focus here is often on regulatory compliance and data security. For instance, multiple hospitals can collaborate on medical research, sharing insights without ever exchanging sensitive patient records. This approach enables breakthroughs in healthcare while respecting privacy laws. Federated learning can also be categorized as horizontal or vertical. Horizontal federated learning involves participants with similar features but different data samples, like multiple hospitals with the same patient data structure. Vertical federated learning, by contrast, connects organizations with different features but overlapping samples, such as a bank and an e-commerce platform sharing customer information. Transfer learning combines both, allowing for central pre-training and local adaptation. One of the biggest advantages of federated learning is privacy preservation. Since raw data never leaves local devices, it's much easier to comply with regulations like GDPR and HIPAA. This approach reduces the risk of data breaches and builds user trust. By keeping sensitive information on your device, federated learning ensures that your privacy is always protected, even as AI models become smarter and more capable. Federated learning allows AI models to learn from a wide variety of data sources, leading to better generalization and reduced bias. By training on diverse data from many devices or organizations, the resulting models are more robust and applicable to real-world scenarios. This diversity helps AI systems perform better across different environments and user groups, making them more inclusive and effective. Federated learning is efficient because it eliminates the need for massive data transfers. Instead, computation happens on edge devices, optimizing bandwidth and reducing costs. This approach is highly scalable, capable of supporting millions of devices simultaneously. By leveraging the power of distributed computing, federated learning makes large-scale AI training more practical and sustainable. With federated learning, models can improve in real time as they interact with actual usage patterns. This means AI systems can adapt quickly to new trends and user behaviors, providing up-to-date and relevant results. Continuous learning ensures that models stay fresh and effective, even as the world changes around them. Federated learning is designed to meet strict regulatory requirements, such as data sovereignty and cross-border data sharing rules. By keeping data local, organizations can collaborate without violating privacy laws. This makes federated learning a future-proof solution for industries like healthcare, finance, and beyond, where compliance is critical. A practical example of federated learning in action is mobile keyboards, like Google Gboard. The keyboard learns from your typing patterns to improve word prediction and autocorrect, but never sends what you type to the server. All learning happens locally, and only model updates are shared. This ensures your privacy while still delivering a smarter, more personalized typing experience. Federated learning is transforming healthcare by enabling medical research across multiple hospitals without sharing patient data. Hospitals can collaborate on disease prediction models and drug discovery, all while keeping patient records within their own walls. This approach accelerates innovation and improves outcomes, while maintaining strict privacy and regulatory standards. In the world of autonomous vehicles, federated learning enables cars to learn from driving experiences without sharing specific trip data. Vehicles can improve navigation and safety by sharing learned patterns, not raw data. This fleet learning approach helps build safer, smarter transportation systems while protecting individual privacy. Federated learning is also making waves in finance. Banks can collaborate on fraud detection, credit scoring, and anti-money laundering efforts without sharing sensitive customer data. This cross-institutional learning strengthens security and improves financial services, all while maintaining strict privacy standards. Federated learning helps optimize smart home devices and industrial sensors by learning from real-world usage patterns. Devices can predict maintenance needs, optimize energy consumption, and improve performance, all without sending raw data to the cloud. This makes smart environments more efficient and privacy-friendly. Social media platforms use federated learning to deliver personalized content recommendations, predict engagement, and improve ad targeting. By learning from user behavior locally, these platforms can enhance user experience without compromising privacy. Only model updates are shared, not your personal browsing history or interactions. Despite its benefits, federated learning comes with challenges. One major issue is communication costs. Multiple rounds of model exchange, require significant bandwidth, and can lead to synchronization overhead and network latency. Efficient communication protocols are essential to make federated learning practical at scale. Another challenge is statistical heterogeneity. Data on different devices may not be independently or identically distributed. This non-IID data can make it harder for models to converge and perform well across all users. Addressing these differences is a key area of ongoing research in federated learning. System heterogeneity is another hurdle. Devices have different hardware capabilities, network conditions, and storage capacities. Some may have limited battery life or intermittent connectivity. Designing federated learning systems that work well across such diverse environments is a complex but crucial task. Security is a top priority in federated learning. Potential threats include model inversion attacks, membership inference attacks, and poisoning attacks. Privacy leakage can occur through gradients, even if raw data isn't shared. Robust security measures are essential to protect both the model and user data. To address privacy and security, federated learning uses advanced techniques. Differential privacy adds calibrated noise to model updates, providing formal privacy guarantees. Secure aggregation uses cryptographic methods, so the server only sees aggregated results, not individual updates. Homomorphic encryption allows computation on encrypted data, offering strong security but with added computational overhead. Looking ahead, federated learning is set to become even more powerful. Technical advancements will bring more efficient algorithms, better handling of heterogeneous data, and reduced communication overhead. Industry adoption is growing in healthcare, finance, automotive, and telecommunications. Regulatory evolution will shape privacy-first AI standards and global frameworks. New applications, from federated reinforcement learning to real-time systems, are emerging. Open-source tools and educational resources are democratizing access, making privacy-preserving AI available to all. Federated learning represents a fundamental shift in AI development from data-centric to privacy-centric approaches. As privacy concerns grow and regulations tighten, federated learning offers a path forward that respects user privacy while still delivering powerful AI capabilities. The future of AI isn't just about building smarter models. It's about building models that are both smart and respectful of our fundamental right to privacy. Great AI doesn't require seeing all your data, just learning from what you're willing to share.